Very well, let us begin chapter 4. So chapter 4 is about methods of proofs in discrete mathematics. The very first type of proof is using the definition to prove a statement, a theorem, or a lemma. Before we begin talking about the use of this type of proof, we need to define some basic definitions, like the definition of even and odd numbers. An integer like n is called even if and only if n equals twice some integer. An integer is called odd if and only if n equals twice some integer plus 1. So mathematically, we can write them this way. N as an integer is even if and only if, double arrows, there exists an integer like k such that n is equal to 2k. N as an integer is odd if and only if, double arrows, there exists an integer like k such that n can be written as 2k plus 1. Let's go over one example together, see what's going on. Use the definitions of even and odd to justify your answers to the following questions. 1. Is 0 even? The second one, negative 301 is odd. Part C says, suppose A and B are integers. Is 6 times A squared times B even? What if we have 10A plus 8B plus 1? Do we consider this number even or odd? E, is every integer either even or odd? The answer to part A is yes. So 0 is considered as an even integer. Why is that? Because there is an integer like 2, that 0 is the outcome of 2 times 0. Minus 301 is odd. Why is that? Because we can write it as the product of 2 times an integer plus 1. How about 6 times A squared times B? Since you can factor out 2, you can write 6A squared B as 2 times K. So obviously, you have an even integer. How about 10A plus 8B plus 1? If you factor out 2 from the first 2 terms, you have 2K plus 1, which is considered as, by definition, an odd integer. E. So for any integer, guys, we're not talking about real numbers. We're talking about just integers. You can classify those into even or odd. So this is always true. Next, definition of prime and composite. We say that an integer like n is prime if and only if that number is greater than 1. So first of all, we do not include 1. And for all positive integers like r and s, if r is the product of those two positive integers, then for sure you can conclude that n is equal to r, or n is equal to s. Mathematically, we can say n is prime if and only if for any positive integer. So note that we are using universal quantifier, r and s. If n is the product of r times s, then r is equal to 1, s equals to n, or r is equal to n, s equals to 1. We say that an integer like n is composite if and only if that number is greater than 1, and if n can be written as the product of two integers like r and s, with the condition that r is greater than 1, s is also greater than 1, they are both less than n. Mathematically, n is composite if and only if there is positive integers r and s, existential quantifier, such that n is the product of r and s, and r is between 1 and n, also s is between 1 and n. Let us take a look at an example. What do you think about 1? Is 1 prime? Is every integer greater than 1 either prime or composite? Write the first 6 prime numbers and also write the first 6 composite numbers. This is a common mistake between students. They think 1 is prime. Take a look at the definition. An integer is prime if and only if that integer is absolutely greater than 1. 1 is not prime nor composite. So officially, you can say that for any integer greater than 1, it's either prime or composite. The first 6 prime numbers, 2, 3, 5, 7, 11, and 13. The first 6 composite numbers, 4, 6, 8, 9, 10, and 12. Next, types of proofs. The first type of proof is not that hard. Existence argument. In this type of proof, your goal is to show that there is at least one element that satisfies the condition. So you have a property and you're looking for one value that satisfies that property. For example, suppose you want to prove that there is existential a solution to the polynomial equation x plus 5 equal to 0. So obviously it's just an algebraic operation. By subtracting 5 from both sides, you can actually find that value. So this existential argument can be proved by solving this equation. For example, suppose you want to prove that there is an even integer like n that can be written in 2 ways as the sum of 2 prime numbers. So can we find that number? Can we find that even integer like n? By inspection, we try to find that number. Take 10, for example. 10 can be written as the sum of 2 prime numbers, 5 and 5. We can also write 10 as the sum of two other prime numbers, 3 and 7. That's it. We just proved part A. There exists, and we found that number. Part B. Suppose R and S are integers. Prove the following. There is existential argument, an integer like k such that 22R plus 18S is equal to k. So we're looking for this k. What is this k value? If we define k to be 11R plus 9S, then we're done. 2 times 11, 22. 2 times 9, 18. So if we define k to be 11R plus 9S, then we're done with the second part. Existential arguments, we found just one instance, just one example that satisfied that condition, and we're done with these types of proofs. Direct proof. So when it comes to direct proof, you try to use the definition and combine them together somehow and deduct the conclusion. For example, prove this statement for all integers. If that integer is even, then its square is also even. How do we prove that? To prove this statement, we have to use the definition of even numbers. First of all, you know that x is even. Your x value is even. So remember the definition of an even number. There is some integers like m such that x is 2m. Your goal is to prove that x squared is also even. So let us raise both sides to 2. You get x squared equals to 2m squared or 4m squared. Then you can factor out 2 and you have 2 times k. So x squared is 2 times k. Using the definition of an even integer, we just proved that x squared is also even. Next example. Prove that the sum of any two even integers is even. Very well. Let us try using the direct definition. Suppose we take two random even numbers. Our goal is to show that their sum is even. So suppose the first even integer is m, 2 times some integer like r. The second even integer is n, which can be written as 2 times another integer like s. So let us add them together, m plus n. m is 2r, n is 2s. You can factor out 2, and you can actually write it as 2 times a new integer k. The sum of two integers, r and s, is a new integer like k. So based on the definition of even integer, the sum of any two integers which are even is even as well. By using the direct definition, we prove this statement. Next example. We can use the direct definition and prove the following statements. The sum of any two even integers is even. The product of any two even integers is even. If you subtract two even integers, the outcome is also even. The sum of any two odd integers are even. The difference of any two odd integers is also even. The product multiplication of any two odd integers is odd. The product of any even integer and any odd integer is even. The sum of any odd integer and any even integer, as you guessed, is odd. The difference of any odd integer minus any even integer is odd. The difference of any even integer minus any odd integer is odd. You can prove all of these statements using the definition. We cannot write down some examples and say, hey, I proved it. That's going to be wrong. You have to use the definition of being even and odd and prove these statements. Very well. Suppose you want to show that an existential statement is false. First of all, recall that the negation of an existential statement is universal. So the negation of there exists is going to be for all. So it follows that to prove an existential statement is false, you must prove a universal statement or its negation is true. Let's take a look at this example to feel more comfortable about this. Show that the following statement is false. There is, so you have an existential statement, a positive integer like n such that n squared plus 3n plus 2 is prime. To prove this statement to be false is equivalent to showing that for all positive integers like n squared plus 3n plus 2 is not prime. Remember the definition of being composite. If you write down n squared plus 3n plus 2 in factored form, n plus 1 times n plus 2, first of all, both of these numbers are greater than 1. None of them is equal to 1. So you can stop at this step and say that, hey, the definition of a prime number says if n is the product of R and S, then either R is equal to n, S equals to 1, or S is equal to n, R equals to 1 for a prime number. Here you see that if you write n squared plus 3n plus 2 in factored form, it's equal to n plus 1 times n plus 2. And none of these two numbers are equal to 1. So n squared plus 3n plus 2 is not prime. negation of, okay, I think I jumped to a different. Let us move on to a new definition. Definition of a rational number. We say that a rational number like R is in the format of a fraction, A divided by B. A and B are both integers, and B on the denominator cannot be 0. Let us take a look at one theorem. This theorem says the sum of any two rational numbers is rational. To prove that, we can use direct definition of rational numbers. So suppose you take two random rational numbers, R and S. Your goal is to show that their sum is also a rational number. Since R is a rational number, you can write R as A divided by B. And B on the denominator is never 0. S can be written as C divided by D. Both of them are integers, and the denominator is never 0. So since our goal is to add them together, let us add these two fractions. Take the common denominator, BD, and on the numerator, you have an integer. Let P be your numerator, and let Q be the denominator. Of course, Q is never 0 because B and D are non-zero integers. So for sure, your denominator is never 0 and your numerator is an integer. By using the definition of a rational number, we just showed that the sum of any two rational numbers is irrational. We can use the definition of rational numbers and then work with even and odd values and prove some statements. Let's talk about divisibility of numbers. Definition: n is divisible by d if and only if n is equal to d times some integer. For those of you who are taking Python or other programming languages, this is equivalent to using divisibility, which is different from mod operator. So these are different from mod or percentage operator. Mod operator gives you the denominator. And the outcome is going to be the remainder. Okay, so let us get back to the definition. N is divisible by d if and only if n equals to d times some integer. N is multiple of d. Or you can say that d is a factor of n. We can also say that d is a divisor of n, or d divides n. These are all equivalent to each other. Mathematically, we write d divides n, and we define it as there is an integer like k such that n is equal to d times k. For example, is 21 divisible by 3? Of course, 3 is a factor of 21. So we can write 3 divides 21. Is 32 a multiple of negative number 16? Of course, negative 16 times negative 2 is 32. So negative 16 divides 32. Very well. Theorem, a positive divisor of a positive integer. For all integers a and b, if a and b are both positive integers and a divides b, then for sure you can say that a is less than or equal to b. Let us try to prove it. Okay, a and b are positive integers. We also know that a divides b. So we have two facts to work with. A divides b. What's the meaning of that? It means that you can find another integer like k such that b is a times k. Since a and b are both positive integers, k must be positive. So k is greater than equals to 1. Let us multiply both sides by a. A is less than equals to k times a, but k times a is equal to b. So we just prove that a is less than equals to b. Another theorem. The only divisors of 1 are 1 and negative 1. 1 doesn't have any other divisors. Okay, perfect. We know that 1 times 1 is equal to 1. Also, negative 1 times negative 1 is equal to 1. Both 1 and negative 1 are divisors of 1. We know that. We already seen this in algebra. Now, suppose you can find other integers like m and n such that their product is equal to 1. First of all, both of m and n are either positive or both of them are negative. So here you have two conditions. M, n are both positive, m, n are both negative. And remember that we don't have any fraction here. No rational number. No rational. For example, you don't have a half times 2 and say, hey, I found these two and it is equal to 1. We don't have any rational values here. All of these are integers. Okay, let us investigate to see what is wrong. Okay, so 1 is equal to m times n. And suppose both of them are positive. Suppose you're investigating this case. M is a divisor of 1. Since m is a divisor of 1, by using the previous theorem, m must be less than equals to 1. Okay, m is a positive integer and m is less than equals to 1, so there is no other choice than m be equal to 1. So m is equal to 1. N must be equal to 1 as well. We have the exact same argument when they are both negative values. The only divisors of 1 are 1 or negative 1. Let us take a look at one example. If a and b are integers, is 3a plus 3b divisible by 3? Can you see 3 as a factor of 3a plus 3b? If you factor out 3 from the expression, of course you see the factor here. So 3 divides 3a plus 3b. B, if k and m are integers, is 10 km divisible by 5, or is 5 a factor of 10 times k times m? Of course you can write 10 in factored form. 5 times 2 times km, and 2 times km is also an integer. So as you can see, you have the factor here. 5 divides right-hand side, 5 divides left-hand side. So 5 is a factor of 10 km. Note that for all integers n and d, d doesn't divide n, or d is not a factor of n if and only if n divided by d is not an integer. For example, does 4 divide 15? Of course not. 15 divided by 4 is not an integer. So 4 is not a factor of 15. Prime numbers and divisibility. An alternative way to define a prime number is to say that an integer like n, which is greater than 1, is prime if and only if its only positive integer divisors are 1 and itself. Let us take a look at one theorem, transitivity of divisibility. Suppose you have two integers, a divides b, a is a factor of b, b divides c, b is a factor of c, then you can conclude that a is a factor of c. We can prove this theorem using the direct definition. Since a divides b, it means that a is a factor of b. So b can be written as a times an integer like r. Since b divides c, it means that c can be written as b times another integer like s. Then here you have b equals to, substitute that b in the second equation. C is equal to AR times S, and as you can see, A is a factor of C. So A divides C. Next theorem, divisibility by a prime. This is a very beautiful theorem. Any integer greater than 1 is divisible by a prime number. Perfect. So suppose you have an integer like n, and n can be written as the product of two other integers like R sub 0, S sub 0. R sub 0 is between 1 and n, S sub 0 is between 1 and n. If you remember, this is the definition of a composite number. If n is prime, you don't have anything to prove. So suppose your n is composite. So n is the product of R sub 0, S sub 0. Now we're trying to find a prime number dividing either R sub 0 or S sub 0. It's like saying that 100 is equal to 4 times 25. 4 is not prime, 25 is not prime. But we can find a prime number like 2 that divides 4, or we can find a prime number like 5 that divides 25. You keep repeating this process until we find that prime number. Okay, perfect. So if R sub 0 is prime, we found a prime number dividing n. If S sub 0 is prime, it means that we found a prime number, which is a factor of n. We don't have anything else to prove, and we stop at this step. Suppose not. Suppose R sub 0 and S sub 0 are not prime numbers. It means that these two numbers are also composite. We can write R sub 0 as the product of two other integers, like R sub 1 and S sub 1. Again, we have to investigate. If R sub 1 is prime, R sub 1 is a factor of R sub 0, and R sub 0 is a factor of n, so R sub 1 is a factor of n, and you're done. If S sub 1 is prime, then S sub 1 is a factor of R sub 0, R sub 0 is a factor of n, so S sub 1 is a factor of n, and you're done. Suppose not, and R sub 1, S sub 1, none of them are prime numbers. We keep repeating this algorithm. It's like a loop, but it has to stop somewhere. You eventually can find a sequence of numbers that one of them is prime. We keep factoring these numbers until we find a prime factor. You have a sequence of numbers, R sub 0, R sub 1, R sub 2, and you have to stop somewhere. It means that any number, any integer greater than 1 is divisible by a prime number. You can assume the easiest example possible, like 100, which is the product of 4 and 25. 4 is not prime, 25 is not prime, but we can write 4 as the product of 2 and 2. So it has a prime factor. We can write 25 as the product of two numbers, which is prime. So by keep factoring these numbers, we can eventually find a prime factor. Next example. Is the following statement true or false? For all integers a and b, if a divides b, b divides a, then can we conclude A and B are equal to each other? This statement is false. Why is that? For example, 2 divides -2, okay? -2 also divides 2, but 2 is not equal to -2. I found a counter example for this statement, and this statement is false. So when this statement is true, this statement is true if and only if A and B have the same sign. True if and only if A and B are both positive or A and B are both negative. Theorem, unique factorization of integers, which says that if you have any integer greater than 1, for sure you can find some distinct prime numbers, p sub 1, p sub 2, p sub 3, p sub 4, p sub k, and some positive integers like e sub 1, e sub 2, e sub 3, e sub 4, e sub k, such that n is the product of p1 raised to e1, p2 raised to e2, p3 raised to e3, and pk raised to ek, like 100, which can be written as 2 squared times 5 squared. This is called unique factorization of integers. Definition: standard factored form of an integer greater than 1. So if you write the factorization in the format that P1 comes first, P2 comes second, P3 comes third, and Pk, the largest number, comes at the end, then we say that we have a standard factored form for integer n. Consider 3300. Our goal is to write this number in standard factored form. The factorization of this number is 100 times 33. 100 is 4 times 25 times 3 times 11. 4 is 2 squared, 25 is 5 squared, and 3 is 3 with power 1, and 11 has power 1 as well. 2 squared, 3 to the first, 5 squared, and 11 to the first power is standard factored form for this number. Very well, using unique factorization to solve the problem. Suppose m is an integer and 8 times 7 times 6 times 5 times 4 times 3 times 2 times m is equal to 17 times 16 times 15 up to 10. Question says, is 17 a factor of m? Okay, you can say that since 17 divides right-hand side, so 17 is a factor of right-hand side, then 17 divides left-hand side as well. Is 17 a factor of 8? No. Is 17 a factor of 7? No. 17 a factor of 6? Of course not. 17 a factor of 5? Nope. 17 is a factor of 4? No. 17 is a factor of 3? Of course not. 17 is a factor of 2? Nope. 17 must be a factor of 5. Or you can divide left-hand side, right-hand side, simplify right-hand side, and show that m has 17 in it. Theorem, the quotient remainder theorem. Given any integer like n and positive integer like d, for sure you can find a unique number like q, another unique number like r, such that n is dq plus r. R as the remainder is between 0 and d. For example, suppose n is 54 and d is 4. Let us find q and r. 54 can be written as 4 times 13 plus 2. So q is equal to 13 and r remainder is equal to 2. Suppose n is equal to negative 54 and now d is just a positive number 4. Negative 54 can be written as 4 times negative 14 plus 2. Therefore, q is equal to negative 14 and r is equal to 2. Finally, suppose n is equal to 54 and d is 70. 54 can be written as 70 times 0 plus itself. So q is 0 and r remainder is the same as n. When you see symbols like n, div, d, it means that the integer quotient obtained when n is divided by d. So d divides n. When you write n mod d, it means that you're looking for your remainder. Mod operator, percent in your programming languages. Representations of integers mod 4. For any random integer like n, if you divide that integer by 4, the remainder is either 0, so this is plus 0, or the remainder is 1, or the remainder is 2, or the remainder is 3. Because of quotient remainder theorem, if you divide n by 4, the remainder is a number between 0 and 4. So any integer divided by 4 has these 4 formats. Theorem. The square of any odd integer has the form 8m plus 1. In previous theorem, we learned that any integer divided by 4 has one of these formats. The format is either 4q, remainder is 0, or 4q plus 1, remainder is 1, or 4q plus 2, remainder is 2, or 4q plus 3, remainder is 3. Let us get back to the theorem. It says it is odd. It means that it's not in the format of 2 times an integer. So for sure you can get rid of these 2 cases. You only have 2 formats to work with, 4q plus 1, 4q plus 3. The square of. So we're squaring each of these and we show that the outcome has form 8m plus 1. N is equal to 4k plus 1. Let us square it. You get 4k plus 1 times 4k plus 1. You get 16q squared plus 8q plus 1. If you factor out 8 from these 2 terms, the outcome is 8 times an integer plus 1. So you have 8m plus 1. What if n is 4q plus 3? If n has the format of 4q plus 3, and if we square it, 4q plus 3 times 4q plus 3, 16q squared plus 24q plus 8, which is 16q squared plus 24q plus 9 can be written as 8 plus 1. Between these terms, numbers, we can factor out 8, and we have 8, an integer like m plus 1. So in either of these cases, your integer has square of the form of 8m plus 1. So as you can see, we're using the theorems that we proved before to prove a new theorem. Very well. Our next step, method of proof by contradiction. Suppose the statement to be proved is false. That is, suppose that the negation of the statement is true. So our goal is to show that there is something wrong with this new statement. Take a look at this theorem. This theorem says there is no greatest integer. Let us use proof by contradiction and prove this theorem. Proof by contradiction, start with suppose not, and the negation of this statement, there is a greatest integer like n. So we are saying that we can find an integer which is the greatest possible integer. Okay? Now suppose I take 1 as another integer and add it to my greatest integer n. So I'm adding 1 to my greatest integer. What's the meaning of that? It means that I found another integer like m, which is greater than my greatest integer. It doesn't make sense. So it means that there is a greatest integer n is a false statement. It means that there is no greatest integer. This method, which is very popular, is called method of proof by contradiction. Another theorem for you. There is no integer that is both even and odd. Okay? How do we prove that? Let us try using proof by contradiction. So how does it work? The negation of this statement. There is an integer which is both even and odd. Proof by contradiction. So I'm saying that I have one integer which is even. So I have one integer like n which is even. So it can be written as 2 times a. And at the same time, I say, hey, this integer is odd. So n can be written as 2b plus 1. b is another integer. Okay, it means that 2a and 2b plus 1 must be equal to each other. What's the meaning of that? If I start solving this equation by subtracting 2b from both sides and factoring to a minus b, which is the difference between two integers, is now a fraction. But it doesn't make sense. On the left-hand side, I have two integers. Their subtraction is definitely an integer. On the right-hand side, I have a half as a fraction. Left-hand side, right-hand side are not equal to each other. This error is caused by contradiction. There is an integer which is both even and odd. So this statement is false. It means that its negation is true. Another theorem for you. The sum of any rational number and any irrational number is always irrational. Okay? Suppose not. Suppose I have irrational number and a rational number and the outcome is rational. Proof by contradiction. There is a rational number like R and irrational number like S, and their sum, instead of being irrational, is rational. Okay, R plus S, by using the definition of a rational number, is rational. So I can find two integers like C and D such that R plus S is C divided by D and D is never 0. I also know that my R is rational. So R can be written as A over B with non-zero denominator. So for R, I write A over B. My S is irrational. I don't have any format for S. And it's equal to another rational number, C over D. Let us subtract A over B from both sides and take common denominator. What does it tell you? It tells you on the left-hand side, you have irrational number, irrational. At the same time, on the right-hand side, you have a rational number. So this statement, this last statement is saying that your rational number is equal to irrational number. It doesn't make sense. There is an error caused by this assumption that the sum of irrational and rational number is rational. So this is false. It means that its negation is always true. Another method of proof is method of proof by contraposition. It means that if you have P, then Q, you can prove it using not Q, then not P. So instead of proving this statement, equivalently you can prove the contraposition, which is not Q, then not P. Let's take a look at one example to feel more comfortable about this. This proposition says for all integers like n, if n squared is even, so this is your P, then n is even. So you're trying to prove P, then Q, which is not easy to prove. Instead, we write its contrapositive, which is not Q, then not P. It means that if n is not even, then n squared is not even. If n is odd, we want to show that n squared is also odd. It's not that hard to prove. For any odd integer, that integer can be written as 2k plus 1. Now, all you have to do is to square it. N squared is 2k plus 1 squared, which is 4k squared plus 4k plus 1. You can factor out 2 from the first two terms. You get 2 times another integer plus 1, which is obviously an odd integer. Since we proved the contraposition, it means that we proved the original statement. They are equivalent to each other. Next, square root of 2 is irrational. we want to show that square root of 2 is irrational. So between all the methods that you learned so far, let us pick one of them and try to prove square root of 2 is irrational. Let us use the method of contradiction. Suppose not. Suppose square root of 2 is a rational number. It means that you can find two integers like m and n such that n is never 0 and square root of 2 can be written as n divided by n. So suppose this fraction is in reduced form. What do I mean by that? Suppose I have 4 divided by 6. I can reduce this to 2 over 3. Reduced form. The greatest common factor of 2 and 3 is equal to 1. This is very important. We're going to get an error because of this condition. So suppose there is no common factor between m and n. GCF, greatest common factor, between m and n is equal to 1. Okay, let us raise both sides to 2. You get 2 equals to m squared divided by n squared. It means that m squared is nothing but 2n squared. What's the meaning of that? It means that 2 divides m squared. Since 2 divides m squared, we already proved that 2 divides m. So m is an even integer. M can be written as 2 times k. Now let us raise m to 2. M squared is equal to 4k squared. 4k squared is 2 times 2n squared. Why is that? Take a look at this. You know m squared is equal to 2n squared. And at the same time, you show that m squared is 4k squared. So 4k squared is equal to 2n squared. What's the meaning of that? It means that 2k squared is equal to n squared. It means that 2 divides n squared. It means that 2 also divides n. But look at this condition. The common factor between m and n is 1. Here we have 2 as the common factor of m and n, which is an error. Where did it come from? It came from the assumption that square root of 2 is rational and it can be written as the fraction of 2 numbers in the reduced form. So this statement is false, its opposite, its negation is true. Another cool example for you. 1 plus 3 times square root of 2 is irrational. Very well, we can prove this by contradiction. Suppose not, and 1 plus 3 square root of 2 is rational. It means that there are 2 integers like a and b such that the denominator is never 0, and 1 plus 3 times square root of 2 can be written as a over b. Let us subtract 1 from both sides. 3 square root of 2 is a over b minus 1. Then let us just take common denominator between these two and divide both sides by 3. On the left-hand side, using previous theorem, you show that square root of 2 is irrational. On the right-hand side, you have a fraction, an integer on the numerator, an integer on the denominator, which is rational. This equality says irrational number is equal to a rational number, which is absolutely false. This is an error. Where did it come from? It came from the assumption that 1 plus 3 times square root of 2 is rational. So this statement is false. It means that its negation is true. And finally, a proposition for you. For any integer like n and any prime number like p, if p divides a, for sure you can say that p doesn't divide a plus 1. How do we prove that? Suppose not. Suppose there is an integer like a and a prime number like p such that p divides a and at the same time p divides a plus 1. Using the definition, a can be written as p times r. Using the definition, a plus 1 can be written as p times s. Here you can subtract the left-hand side and right-hand side from each other. You get a plus 1 minus a, which is equal to 1, equals to p times s minus p times r, which is p times r, s minus r. So you have p times s minus r equals to 1. What's the meaning of that? It means that 1 is the product of p, a prime number, and s minus 1. Remember, we proved this. Factors of 1 are 1 or negative 1. So it says p is 1, s minus r 1, or p is negative 1, s minus r is negative 1. P as a prime number is always greater than 1. So none of these can be true. This is an error. Where did it come from? It came from the assumption that there is an integer like a and a prime number like p, that p divides a plus 1. This is false. It means that its negation is true. The last theorem, the set of prime numbers is infinite. It means that prime numbers, they don't stop. They continue to grow. Proof by contradiction. Suppose not. Suppose you have a sequence of prime numbers and actually stops somewhere. Suppose n to be the product of all prime numbers plus 1. So you're multiplying these numbers from your sequence and you add 1. Of course, n is greater than 1. So what's wrong with this assumption? What's wrong with this statement here? Take a look at this. If p divides a plus 1, then p doesn't divide a plus 1. You know that p divides 2 times 3 times 5 times 7 because p is a factor of this product. So based on the previous theorem, p cannot divide n. We have that from previous theorem. 3 times 5 times P. So P doesn't divide N. For sure you know this using previous theorem. Now take a look at your number N. Of course, N as a number is divisible by some prime, let's say Q. And note that you assume the set of prime numbers stops somewhere. So Q is a prime number equal to one of these prime values. Therefore, Q divides this product. So Q divides 2 times 3 because it's one of the numbers in between. You can find Q in between. So what's wrong here? Q divides the product using previous theorem. Q cannot divide N. But we just assume that Q is a prime number dividing N. So there is contradiction. This error came from the assumption that the set of prime numbers stop somewhere. So this assumption is false. Suppose not it's false. So its opposite, which is our theorem, it's always true.